equation or the Bernoulli's equation. Sometimes it is also called as simple bending equation. Or Bernoulli's equation. So to derive the equation, let us consider a beam Now, I'll consider two sections. Two sections, that is AC and BD. Between these sections, let me take a layer along the neutral axis of the beam. Okay, I'm taking a layer along the neutral axis of the beam. This is the neutral axis. Along the neutral axis, I have considered a layer, say EF, in the beam. Okay. Now let me consider one more layer, GH, at a distance y from the neutral axis. I considered one more layer, GH, at a distance y from the neutral axis. Now assume that this beam is subjected to bending. Now I'll write the diagram of the bent beam. Okay. Okay, this is the bent shape of the beam. So here comes the section AC, section AC, and here we will get the section BD. Okay. Now the neutral axis will be EF, EF, and GH. Now, after the beam being subjected to bending, I will write the points E and F as E dash and F dash, and here G dash and H dash. Okay. Now this AC and BD will form a curve of with some angle subtended between the AC and the BD. Let me extend this line. Let me take this angle subtended between the AC and BD as the angle pi. The angle pi. Okay. Let me change the notation as A dash B dash. Okay. A dash B dash C dash and D dash. Now let us assume R as the radius of curvature. Radius of curvature of the layer E dash F dash. Okay, which is taken along the neutral axis. Which is taken along the neutral axis. Okay. Now the length E dash F dash can be measured as the length E dash F dash will be equal to the radius multiplied by angle subtended between the points E dash F dash. We know the equation for length of a curve. If there is a curve of radius R with angle theta inside, okay, the length of this curve, okay, L will be equal to R into theta. Now we are measuring the length E dash F dash. Similarly, we get the equation as R into pi. R into pi. Okay. Now we all know that if there is neutral axis, if we consider the stress along the neutral axis, the stress along the neutral axis will be always zero. Stress along the neutral axis will be always zero. Therefore, there will be change in the layer GH. There will be some increase in layer GH, that is G dash H dash. When you compare the length of G dash and H dash to that of length GH, there will be some increase in the length, but there will not be any increase in the length of E dash F dash compared to the length EF, because whatever the layer we have considered, whatever the layer EF we have considered, that layer is along the neutral axis. You might have studied the stress strain distribution of the beam. So at bottommost layer we will get the tensile stresses, and at topmost layer of the beam you will get compressive stresses, compressive stresses, and at some particular point on the beam there will not be any compressive stress or the tensile stress. The stresses will be zero at this point. When the stresses are zero, there won't be any strain in the at that point. Okay, strain is also zero, or the increase or decrease in the length at that layer will be zero. Therefore, we can write the length EF. Okay, the length EF is equal to length E dash F dash. Okay, as EF as the layer EF considered is along neutral axis. So we can write as length EF is equal to length E dash F dash. Okay, length EF is equal to length E dash F dash is equal to R into pi is equal to R into pi. Okay, now in the next step, what we will do, we will measure the strain in the length GH. Okay, obviously, whatever the layer GH we have considered, it is not along the neutral axis. Definitely, there will be some strain happened to the layer GH. Now, let us measure the strain in the layer GH. Okay, strain in layer GH is equal to strain in layer GH is equal to, so we know that strain is nothing but the change in length divided by original length. Okay, change in length, how we can measure? It is the final length minus original length divided by original length. Okay, strain is equal to change in length divided by original length, and that change in length we will get as final length minus original length. Final length is G dash and H dash. G dash and H dash is the final length minus original length is GH divided by original length, again it is GH. Okay, so if you refer this figure 1, the length GH is equal to length EF, correct? The length from figure 1 we can write from figure 1, the length EF is equal to length GH, which is equal to length EF. We have formulated the equation for EF as R into pi. I can write here R into pi. Okay. And similarly, length G dash H dash, I can write from figure 2. I will call this as figure 2. Figure 2. The length G dash H dash can be written as, so here the distance of the neutral axis from the layer G dash H dash is Y. We have considered that layer at a distance Y, correct? So here the distance is Y. So the length of G dash H dash can be taken as the radius R plus Y into pi. Similar to the equation of the length of curve. Okay, similar to the equation of the length of the curve is equal to G dash H dash is equal to G dash H dash is equal to R plus Y is the radius and pi is the angle subtended. Therefore, R plus y into pi. Okay, similar to the equation of the length of the curve as I explained earlier here. Okay, length g dash h dash is equal to r plus y into pi. Okay, now you substitute the value of gh and g dash h dash values here in this equation. Okay, so we will get the strain in layer gh is equal to, therefore strain in layer gh is equal to g dash h dash r plus y into pi minus gh is nothing but r pi divided by r into pi. Okay, now simplifying this, r into pi plus y into pi minus r into pi whole divided by r pi. R pi gets cancelled in the numerator. So we'll get the equation as y into pi divided by r into pi. Okay, pi gets cancelled again. The final equation is y by r. Okay, y by r, which is strain in layer GH. Okay, now we got the strain in layer GH. We know the equation for the Young's modulus. We know that. Modulus of elasticity is equal to stress by strain. Okay, here the stress is nothing but bending stress in this case. Okay, in this particular case, stress refers to the bending stress in the beam. Okay, and bending stress will usually represent by the letter F. Okay, therefore E is equal to bending stress F divided by strain. Therefore the strain will be equal to F by E. Okay, now you call this strain in layer GH as equation number 1. This has equation number 2. Okay, so we have the generalized equation for strain as F by E. We know the strain in layer GH, which is equal to y by r. Now by equations 1 and 2, from equations 1 and 2, we can equate the strains. Y by r is equal to F by E, or F by E is equal to y by r. Okay, we can rewrite as F by y is equal to E by r. We'll call this equation as equation number 3. Okay, now in the next step, I'll consider some elemental area in the beam at a distance y from the neutral axis. Okay, let me write the cross section of the beam. This is the neutral axis. Okay, now I'll consider an elemental area dA at a distance y from the neutral axis. Okay, So this is the cross section. If I write the longitudinal section, so this is the longitudinal section. Okay, so here we have taken an elemental area at a distance y from the neutral axis. Okay. Now we know that the equation f by y is equal to E by R. Let me take the same equation, previous equation, whatever we have derived. F by y is equal to E by R. Therefore, the F becomes equal to the stress, bending stress becomes equal to E by R into Y. E by R into Y. Okay. Now, in the second case, what we have done is we have taken an elemental area dA at a distance y from the neutral axis, at a distance y from the neutral axis. Now, what we will do, we will calculate the resisting force at this elemental area dA. Okay. The resisting force, the resisting force at elemental area is equal to it is a multiplication of stress into area of cross section of elemental area. Correct. So whatever the equation we have derived, F, that is the bending stress equation. Okay. At elemental area dA, we have the F as stress which is acting, that stress multiplied by cross sectional area dA will give the resisting force. Stress is nothing but resistance to the resistance per unit area. Correct. Stress is nothing but resistance per unit area. So if you multiply that stress with the area, you will get the resisting force. Correct. Therefore, the resisting force we can write as the stress or the bending stress into cross sectional area. Stress multiplied by area of elemental strip, which is equal to F into dA. F into dA. So F is nothing but E by R into Y into dA. Now we got the resisting force through the elemental area. Resisting force through the elemental area. Now we will take moment of this resisting force. Okay. Moment of this resisting force about the neutral axis. Okay. Moment of resisting force about the neutral axis is equal to moment of a force is nothing but force into perpendicular distance. Correct. Force is E by R into YdA. E by R into YdA. This is the force into perpendicular distance. We are taking moment of resisting force about the neutral axis. That resisting force is acting through this elemental strip. Okay. So from this resisting force, the distance of the neutral axis is y again. Okay. So moment of resisting force about neutral axis is equal to magnitude of the force, that magnitude of the resisting force multiplied by perpendicular resistance. Perpendicular resistance is again y multiplied by y. Okay. So therefore it is E by R into y square dA. E by R into y square dA. Now we got moment of resisting force about the neutral axis. Okay, moment of resisting force which is acting at the elemental area dA about the neutral axis. If you want to get the total resisting force from the full cross section, you need to do the integration. Okay, therefore total moment of resisting force about neutral axis is equal to, I will write as sigma into E by R into y square dA. Okay, so this equation gives the moment of resisting force which is acting at the elemental area dA about the neutral axis. If you want to get the moment of the full area or the moment of the full resisting force which will come from the full cross sectional area about the neutral axis, it will be summation of moments of such resisting forces by considering similar type of elemental areas. Okay, sigma into E by R into y square into dA. Okay, now I can write this equation as E by R into sigma into y square dA. Okay, because the Young's modulus and the radius of curvature both are constants. So the variable parameters are only the y, distance of the neutral axis from the uh, fiber whatever we have considered, and the cross sectional area dA. Okay, therefore it is sigma into y square into dA. Okay, now this sigma into y square into dA can be replaced by the moment of inertia. Okay, we know that moment of area is area into perpendicular distance. Okay, nothing but dA into y will give moment of area. If you find moment of an area, or if you find second moment of area, it will be dA into y square. That second moment of area is nothing but moment of inertia I. Okay, so area multiplied by distance square will give moment of inertia. Okay, or the second moment of area, the moment of an area will give is termed as moment of inertia. Therefore we can rewrite the above equation as E by R into I. Okay, now I'll take moment of resisting force about the neutral axis as M dash. Okay, I'll take moment of resisting force about the neutral axis as M dash. Okay, now we have derived the equation for moment of resisting force about the neutral axis, that is E by R into Y. Okay, now to maintain the equilibrium, whatever the moment which is acting on the beam should be equal to the moment of resistance or the moment of resisting force about the neutral axis. Okay, Here M is moment due to externally applied load. M dash is moment of resisting force. Okay, moment of M is moment of acting force, M dash is moment of resisting force. Okay, to maintain the equilibrium, whatever the moment acting should be equal to moment resisting. Therefore, what I will do, I will replace this M dash by M now in the next step. Therefore, M is equal to E by R into I. E by R into I. Okay. Therefore, I'll take this moment of inertia I to the LHS. What we'll get is M by I. M by I is equal to E by R. M by I is equal to E by R. Now we will call this equation as equation number 4. Equation number 4. Now referring to equation number 3 and 4. Okay. F by Y is equal to E by R and M by I is equal to E by R. We can write as M by I is equal to E by R is equal to F by Y. Okay, this equation is called as bending equation or Bernoulli's equation. Bernoulli's equation where M is the moment acting on the beam due to externally applied loads, and I is moment of inertia. I is moment of inertia. Then E is Young's modulus. Young's modulus. Then R is radius of curvature of neutral axis. Radius of curvature. Then F is bending stress. F is bending stress. Then Y is distance of extreme fiber from neutral axis. Distance of extreme fiber from neutral axis. Okay. So this is the required equation, bending equation, that is M by I is equal to E by R is equal to F by Y.